All right, let's dive right into this explainer. Today, we're going to talk about how to transform a vulnerable Linux server into an absolutely impenetrable digital fortress. Because here's the reality. When you first deploy a standard Linux distribution, those default settings, they are almost always optimized for maximum compatibility and ease of use. They are definitely not optimized for maximum security. But we are going to change that dynamic completely.
So, we're going to explore a really specific core challenge here. How do you secure your system at the lowest possible level without taking your critical applications offline? I mean, in a production environment, you simply cannot afford downtime every single time you need to patch a vulnerability or close off a potential attack vector. We need a way to, lock the doors and raise the shields while the ship is still flying.
And syscontrol gives us exactly that capability. It is quite literally a live control panel that lets you toggle security features instantaneously. The way it works is by modifying kernel parameters directly, right there in the virtual /procs/sys directory. You can really think of it as accessing the master switchboard for your operating system's brain. It gives you this incredibly granular control over your network, your memory management, and process handling, all completely on the fly.
So here's the blueprint for our fortress. We'll kick things off with Section 1, the Systel threat model. Then we'll build our outer moat in Section 2 with network defenses. After that, we reinforce the inner walls in Section 3 with kernel hardening, lock down the vault in Section 4 with file system protections, and finally, wrap it up in Section 5 by tying off some loose ends.
Let's start with Section 1, the syscontrol threat model. Because deploying security controls in a vacuum without understanding how they impact your system is just a recipe for disaster.
As this thesis from Karlstad University points out, the real balancing act is selecting security measures that don't absolutely crush the performance of your resource-constrained systems. I mean, a hardened server doesn't do you any good if it's too slow to actually serve its clients, right? But the fantastic news from their research is that applying sysctl kernel hardening introduced only a tiny 2.41% latency overhead in their benchmarks. That means we get massive security gains with practically zero performance penalty. Moving right along to Section 2, Layer 1, our network defenses. This is our outer perimeter. And frankly, it is by far our biggest attack surface because it's where your server interacts with the chaotic, completely untrusted environment of the public internet. Under the net umbrella, your network defenses really break down into two main buckets: preventing spoofing and surviving denial-of-service attacks. We also need to make sure we aren't accidentally acting as a router, so turn off IP forwarding unless your box is explicitly acting as a VPN or a NAT. The logic here is simple. If we strictly control who is permitted to talk to us and prevent them from overwhelming our resources, we literally win half the battle before an attacker even gets close to our applications.
So let's look at the anti-spoofing parameters. These act as the drawbridge to the fortress, making sure only traffic with legitimate, validated origins can approach. By setting RP filter to 1, we turn on strict reverse path filtering. It just instantly drops incoming packets if their source IP looks faked. Setting accept source route and accept redirects to 0 guarantees that malicious actors cannot dictate how your traffic is routed. And toggling log Martians to 1, that ensures any mathematically impossible packets are logged right to your intrusion detection systems for analysis.
But, what happens when the enemy just tries to flood the moat? What if they overwhelm the server with a barrage of incomplete TCP handshakes? That is your classic SYN flood attack, and it's designed to completely exhaust your server's connection queue so that your actual, legitimate users can't get through. And this is exactly why the TCP sync cookies parameter is an absolute game changer. It makes sure we do not commit any system resources until an incoming connection proves it's real. When you set this to 1, the kernel starts using cryptographic hashes to verify the connection instead of consuming memory for a pending queue. It basically lets your server just ride out massive floods without even breaking a sweat.
All right, on to Section 3, Layer 2 kernel hardening. If an attacker somehow bypasses those network defenses or compromises a local application, the kernel.parameters dictate the kernel's self-protection. It's your last line of defense. To really understand why tuning the kernel matters, just look at a devastating real-world exploit like CVE 2023-2163. This was a massive flaw in the Extended Berkeley Packet Filter, or eBPF. Now, eBPF is a brilliant, highly powerful tool built right into the Linux kernel. But vulnerabilities here are exceptionally dangerous.
Basically, this complex flaw tricks the kernel into bypassing its own security checks. This allows local attackers to read and write arbitrary kernel memory.
Someone could exploit this miscalculation to escalate their privileges straight to root, or even completely escape the isolation of a Docker container.
But here is the wild part. Setting the parameter kernel.unprivilegedbpf disabled to just this single number, 1, completely neutralizes that threat, and you don't even have to reboot. By flipping that switch, you revoke access to the BPF system from unprivileged users, instantaneously cutting off a massive exploit primitive. It's one tiny knob that provides massive protection.
Next, we structurally reinforce our walls using ASLR. We replace a predictable static memory layout with a highly randomized one that exploits simply can't guess. By setting randomized VA space to 2, the kernel actively scrambles the location of the stack, your executable code, and libraries. Empirical research shows this introduces up to 31.8 bits of entropy. So when an attacker fires off a payload, they are forced into a literal blind game of chance. It dramatically increases the likelihood that their exploit will just crash the process instead of taking over your system.
Furthermore, we have to blind the attackers by stopping information leaks. An attacker desperately relies on these leaks to map out the system and bypass things like ASLR. So, hiding kernel memory addresses with kptr_restrict and locking down the message buffer with dmessag_restrict effectively starves them of that critical intel. Meanwhile, setting Yama's ptrace scope to 1 stops a compromised application from attaching a debugger to snoop on memory. Oh, and as a quick bonus, disabling the sysarc key ensures that a physical attacker can't just use magic keyboard combos to compromise the kernel.
That brings us to Section 4, Layer 3, File System Protections. We've reached the absolute center of our fortress, where we protect the fs.subsystem, because even with the hardened network and kernel, sloppy file system permissions can still hand an attacker an easy win.
These straightforward parameters act like vault locks. They completely shut down classic file system tricks, preventing malicious symlink routing and stopping the system from accidentally dumping secrets. Protecting symlinks and hard links ensures attackers can't trick privileged programs into overwriting your critical files. And setting suid dumpable to 0 is absolutely vital. It makes sure that if a highly privileged program crashes, it won't just dump a core file onto the disk containing unencrypted passwords or keys straight from RAM.
Finally, let's look at Section 5, Tying Off Loose Ends. We're going to wrap up this explainer by addressing memory management and some unused protocols. For instance, in the memory subsystem, adjusting vm.mmap_min address does a great job blocking null pointer exploits. But we also really need to address protocols that are active by default but that you might be completely ignoring. Specifically, IPv6. Look, if you aren't actively using IPv6, it's just an unguarded backdoor. You can follow these simple steps to ignore router advertisements, disable the protocol entirely, and persist those settings. So many admins build this perfectly secure IPv4 stack while completely forgetting that IPv6 is just quietly listening in the background. And once you have tuned all these parameters, the single most important step is to write them to a config file inside the /etc/sysconval.d directory. That guarantees your fortress rebuilds its defenses automatically every time the server reboots.
And remember, the absolute best part is that all of this can be applied instantly using the command systotal-p. You harden your infrastructure entirely on the fly. You load that persistent file into the live kernel, and the changes are active in literal milliseconds. No service interruptions, no scheduled maintenance windows.
Which leaves us with one final, pretty provocative thought to take away from this explainer. If you aren't actively tuning these security knobs on your servers, who is? Default settings are practically an open invitation to modern attackers. By taking control of systeal, you take ultimate control of your infrastructure's fundamental security posture.